Alright. Hi, so we do an example of a one-dimensional problem. And so what I've shown, we've got three charged particles, Q1, Q2, and Q3. Put their values here, 3 microcoulombs. This is minus 1 microcoulomb, and this is positive 2 microcoulombs. Here are the distances between them. So I just place the origin on Q1. Q2 is at 3 meters. Q3 is at 5 meters. And what I want to know is the force on charge 2. So we want to know the force on this middle charge due to the other two charges. So what we're going to do is we're going to calculate, I'm going to write this down, at the force on 2. This is going to be F21 plus F23. So again, the subscripts, this means the first one refers to the object, the second refers to where the force is coming from. So we have the force on 2 due to 1 plus the force on 2 due to 3. And we calculate these forces separately. So when we calculate F21, that's a force just between 1 and 2. We pretend Q3 does not exist. And then we calculate F23. These are the only two forces we're looking at. We pretend Q1 doesn't exist. And so now we're dealing with vectors because forces are vectors. However, because it's a one-dimensional problem, we can deal with the direction just with a plus and minus sign. So let's look at F21 first. So here's Q2. I'm going to actually write this. Here's like a free body diagram. This is Q2. So the force of interaction between charges 1 and 2, well, charge 2 is attracted to charge 1 because it's negative. It's attracted to this positive charge. So F21 is going to point to the left. And then if we look at the interaction between 2 and 3, charge 2 is attracted to charge 3. And so it's going to point in this direction. And so to find the force overall, we're going to find these magnitudes. But again, they're going to add very simply because they're both on the same line. So it's like we can just say this one's positive, this one's negative, and then just add them as numbers. Actually, what I'm going to do is I'm going to move this picture over here just to clear up a little room. So this was F23, and this is F21. Okay, so let's start out by calculating F21. We have K, our constant. Okay, and now we have Q1 times Q2. So we have 3 microcoulombs times, okay, now this is an important point. I'm going to write this out. I'll just write it out. Sorry, let me do this off to the side for a moment. 3 microcoulombs. That's equal to 3 times 10 to the minus 6 coulombs. Now, I like positive exponents, so you can also write that as 3 coulombs divided by 10 to the 6. That's the form I like it in. So here we have 3 microcoulombs, that's Q1. I'm going to write it this way. And then we have Q2, which is minus 1 microcoulomb. I'm going to write that as 1 coulomb over 10 to the 6. I am definitely not going to include that minus sign because we're just calculating the magnitude of the force. We already know the direction. Now, the reason I'm really emphasizing this is because that if I plug in the minus sign, that would give us a negative number. But that doesn't tell us what direction it's pointing. We have to look at this picture to see, like F21, we know it's attracted to Q2 is attracted to Q1, so that force is going to be to the left. Now, the minus sign, if you do it a certain way, that minus sign can tell you kind of what direction something is pointing, but we're not doing it that way. So we're just calculating the magnitude. We definitely don't want to put that minus sign in there. And again, sometimes students see like, okay, it's a negative, that means it's to the left, because we say right is our positive direction, but that is not always going to be the case. So like for an example, let's say we calculated F23. The product Q2 times Q3 is going to be negative. However, this force is pointing to the right. So, yeah, just really be clear on that. We are only calculating magnitudes here. Okay, so we do not put the minus signs in there. Now, we have K, Q1, Q2. Now we divide by the distance squared. The distance between them is 3 meters. So I'm just going to square that right off the bat. Okay, and actually this is something you definitely do not need a calculator for. The 9 cancels out, meter squared cancels out, coulomb squared, yeah, we're good there. So what we have left is 3 times 10 to the 9th and a Newton. And on the bottom, we have 10 to the 12th. And just because it'll work out nicely, 10 to the 1,000 millinewtons is equal to a Newton, and then the exponents cancel out as well. 10 to the 9 times 10 to the 3rd is 10 to the 12th. And so the force of interaction between these two objects is 3 millinewtons. I guess we can just leave that up here. Doesn't look nice though. Let's here. So F12 is 3 millinewtons. Okay, now let's calculate F23. Now here we have F21. Here I wrote F12, doesn't matter, because we're just talking about the magnitude. And, you know, F12 equals F21 by Newton's third law. So yeah, let's calculate the force of interaction between 2 and 3. So kind of just doing the same as before. We have our constant. And then we have Q2, which is 1 microcoulomb, or 1 coulomb over 10 to the 6. We do not put the minus sign. And then we have 2 microcoulombs. So it'll be 2 coulombs over 10 to the 6. Now we're dividing by the distance squared. The distance between these is 2 meters. We're going from 3 to 5. And so if we square that, we get 4 meters squared. And just because I know we're going to use this, let's get the same units. 10 to the 3rd millinewtons in 1 Newton. So if we go through the units here, Newton cancels, coulomb squared, that gets rid of those. Meters squared cancels that. So what we have is 9. Oh, well, let's also do this. 10 to the 9 times 10 to the 3rd is 10 to the 12. 10 to the 6 times 10 to the 6, 10 to the 12th, they cancel. So working in millinewtons works out really nicely here. So here we have 9 times 2, this is 18. And on the bottom we just have 4. So this is 9 halves, or 4.5. So F23 is 4.5 millinewtons. And again, both of those numbers are just magnitudes. We know what direction they're pointing. So overall, the net force on mass 2, we have 4.5 to the right, 3 to the left, So the net force is just 1.5 millinewtons. And that's it. So again, there are a lot of steps here and a lot of ways to screw up problems like this. The one thing that always applies to any physics problem, pay attention to units, that's very important. And then just be very careful that you get the procedure right because there's a lot of steps. So some common mistakes are plugging in the minus sign and just getting confused in the direction. Also, something I've seen students do, like here, like the force between Q and 3, I've seen students put in a problem like this, like 5 meters instead of 2 meters. So we want the distance between the two charges. You don't plug the coordinates of the point in, but I have seen that done. So just, watch out for things like that. Again, I mean, little things, but it makes a huge difference in the end. And yeah, I guess that's it for a one-dimensional problem. And I'll do a separate video on a two-dimensional problem where it's kind of the same procedure. The main difference is forces are not going to be lined up anymore. And so there's just extra steps involved when it comes to adding the vectors. So that'll be a separate video on that one. So that'll be it for now.